Today, I'm very happy to introduce Satish. He did his PhD at the University of Leiden, and nowadays he's a postdoc at our institute. He works with gravity and in particular in deriving exact analytic solutions. The title of his talk today is Spin-induced Motion in Black Hole Spacetime. Thanks a lot, Satish, for accepting our invitation. And if there are questions, please raise your hand. You'll also be checking the.
Are we recording already? Thanks.
Okay. So, please, Satish, when you.
Yeah. So can I go?
Yeah.
Great. So let me share the screen. Just a moment. Share. Can you see my slides?
Yes.
Can you see it now?
Yeah.
Okay, great. Okay, so thanks for the invitation, and it's my pleasure to talk in my parent organization, IIP. So today I will talk about the spin-induced motion in black hole spacetime. So basically, it's about the spinning particle dynamics within the framework of general theory of relativity. And all the content which I cover in this talk is published in this paper, archive paper last night. So, yeah. So the spin is an indispensable property of astrophysical objects, as we all know, and even for microscopic objects as well. So the understanding of spin, or attempt to understand the spin of a macroscopic object, has begun very soon after the invention of the general theory of relativity. For example, Matthews and Pepper-Petro started formulating their theory for understanding the spinning particles since 1937. The initial papers started from 1937. And around 1975, so after the discovery of this rapidly rotating neutron star, a new approach based on non-geometrical semi-relativistic approach, based on the swing-West-Thorst theory, whereas this Matthews and Pepper-Petro is a GR approach. And very recently, in 2015, myself with two other collaborators, D'Ambrosi and Van Houten, has given a new formalism for describing spinning test bodies in curved spacetime based on the covariant Hamiltonian approach. And immediately we solved for a very simple case. We solved for the circular orbit in Swatchet. After that, we extended our formalism to the case of Reisenautsum with Jorinder van de Vis, and it has been published in PRT in 2016. And now, currently, with the help of IIP postdoc, I'm fortunate to extend this framework and develop it for the Kerr spacetime, which is more complicated. So I developed for the Kerr spacetime. I alone developed this, and I published it in archive, and it appeared in archive last night as given in this link. So now, before we try to understand the spinning particles, let us recap and understand the test particle in the Hamiltonian approach. In the Hamiltonian approach, there are we need three sets of ingredients. One is phase space, which identifies the dynamical degrees of freedom, whereas in the case of test particles, it is only position and the covariant momentum pi mu. And the second one is the Poisson-Dirac brackets, which defines the symplectic structure for these coordinates. And the third one is the Hamiltonian, which describes the evolution of the system. So these are the three ingredients which describe the dynamics of test particles in curved spacetime. Being defined, the phase space and Hamiltonian, it is very straightforward to compute the equations of motion by computing the Poisson-Dirac brackets of these phase space coordinates with the Hamiltonian. We obtain the equations of motion. We could see that the pi mu is nothing but the covariant momentum, as we said, which is proportional to the proper forward velocity. And the second equation is nothing but the famous geodesic equation. So this is the it's very straightforward to obtain the equations of motion here. And suppose if we want to solve these equations of motion in a particular space-time, let's say Schwarzschild or Kerr or whatever, then we need conserved quantities to solve it analytically. For example, the Hamiltonian itself is a universal constant, which can be expressed like this. And in addition to that, based on the symmetries of the space-time, which we are interested in, then we get some additional conserved quantities J. The condition should be that the conserved quantity should with the brackets, it should obey this condition. So this is for spinning particle. This is for the test particle. Now, in case of spinning particles, the spin tensor is described, is described with the real antisymmetric spin tensor field as given here, where the sigma mu has 6 components. 3 of them are magnetic type dipole moment, where here in this case is nothing but the internal angular momentum S mu, and it's a pseudo vector. And the remaining 3 are electric type dipole moment, whereas in the gravitational context it is called as mass dipole moment or Z mu, which is a real vector. And this S mu and Z mu, by construction, they should be space-like. And in addition to that, we have this U mu, which is a time-like unit vector. And these are required to match the number of independent components of the spin tensor sigma mu. Right? So being defined the spin tensor, now let us look at the phase space. So the phase space of the spinning particles has 3 quantities here: the position coordinate x mu and the covariant momentum pi mu and the spin tensor sigma mu. So now we compute these covariant Poisson-Dirac brackets for different combinations of these dynamical degrees, and it is given here. And this is formulated based on the condition that these dynamical quantities should obey the Jacobi identities and the Casimir invariant as given here. And the most important thing is these brackets are model independent, which means we can choose any Hamiltonian irrespective of these brackets. Suppose for our analysis, let me choose this minimal Hamiltonian. That is, I consider the particle interacts only gravitationally. There are no external forces like Stern-Gerlach force or any other fields. So then this is the minimal Hamiltonian. Then now I compute these phase space coordinates x mu, pi mu, sigma mu with this chosen Hamiltonian. Then I obtain the equations of motion. The first equation is same as that of test particle, which says that the covariant momentum is proportional to the proper forward velocity. And the second equation, the left-hand side is nothing but the geodesic part. And the right-hand side, suppose if you replace this spin with charge and this Riemann tensor with electromagnetic field strength, then this is the Lorentz force, the electromagnetic Lorentz force, right? So in analogy, this is called as gravitational Lorentz force. The spin interacts with the Riemann tensor is called as gravitational Lorentz force. And the third equation implies that the world line is a curve in space-time along with the spin tensor is covariantly constant. So this is again analogous to the conservation of charge, so to say. So these last 2 equations are my 10 coupled first order differential equations, which I need to solve it to understand a spinning particle in any particular space-time. So before going into solving this particular space-time, we should also note that the Pirani vector Z mu, which we defined in the spin definition, it cannot be imposed equal to 0 all the time. Maybe in the initial rest frame, it can be equal to 0, but throughout the motion, it evolves with the proper time evolution equation as shown here. Look at this world tube where this thick black line is the world line where the spin tensor is covariantly constant, shown by these black arrows. And these dotted lines are some center of mass world lines. And the difference between my world line, which is this thick black line, and the center of mass world line is Z mu. and this is not equal to 0 all the time, right? So now, before going into solving it, let us collect the constant of motion because it will be very useful for dealing it analytically. As Noether theorem implies that there are conserved quantities results from the symmetries of space-time. This J comma S0, the conserved quantity which satisfies this condition is given like this for spinning particles, where this x mu is nothing but killing vector on the space-time, and beta is the anti-symmetrized gradient which couples with the spin tensor, and this x mu and beta mu nu should obey these conditions. And in addition to the space-time symmetries, conserved quantities, there are a universal constant, like similarly for test particles. The Hamiltonian itself is a universal constant. And here, additionally, we have total spin I, which is defined like this, and the pseudo-scalar spin dipole product, which is D, which is again defined like this. And this is going to be very useful. These conserved quantities are going to be very useful for dealing this problem. So now let us start solving it in the Kerr spacetime. So it should be a simplest orbit. So as we all know that the Kerr metric as given by gives us the rotating vacuum solution of Einstein's field equation, and it is written in Boyer-Lindquist coordinates as shown here, where A is nothing but the total angular momentum per unit mass of the black hole, or otherwise called as Kerr parameter, and this rho square and delta square of some notations used throughout the calculation. So in the planar case, in the equatorial plane, the Kerr metric is axially symmetric in the rotation, as well as the metric is time independent. So these two qualities, suggest us two killing vectors in the equatorial plane, as given by these two killing vectors, alpha t mu and alpha pi mu. Being defined this, it's very handy to obtain the conserved quantities. The total conservation of energy and the total conservation of angular momentum. For our calculation purpose, we scale it with the mass of the particle, the spinning particle small m, which is of course constant. So E by m and Jz by m, call it as epsilon and eta, right? So now let us look into the equatorial plane. So let us choose the direction of the total angular momentum as the z axis, which means the theta is pi by 2, therefore pi theta will be 0, which implies there is no motion perpendicular to the plane. Therefore, all the theta components of the spin tensor is 0. And in addition to that, from our equations of motion, I obtained that sigma t phi is also equal to 0. So therefore, instead of, out of 6 spin components, I am left with only two of them, sigma tr and sigma r phi. We will come to that later. Which is given here in the conserved quantity. It's only sigma tr and sigma r phi. We are only left with these two in the plane. So this condition implies that the directions of orbital and spin angular momentum must be separately preserved. So as a result, we get a theorem stating that, when a spinning particle is orbiting in the Kerr plane, the direction of the spin of the particle must either align parallel or anti-parallel with respect to orbital angular momentum. So there are the other possibilities are not, it's not allowed. So which means the planar motion requires alignment of spin with the orbital angular momentum. So this we obtain as a result from our calculations. So this is not an assumption, we get it as a result, first result. So being obtained that, now we use these conditions, these spin conditions, and these two conserved quantities in our original equations of motion, which are these 10 equations. By using this, we can get rid of 9 equations, and we are left with only one, as shown here. The remaining equation will be of this form, where omega phi is the azimuthal frequency, and xyz are nothing but constants, which are functions of radius of the orbit and spin of the particle and spin of the black hole. So now we can straight away write the solution for the azimuthal frequency of a spinning test particle in the Kerr plane, which is the quadratic equation, which is very straightforward to write. And in this, the plus or minus indicates that the spinning particle can align either parallel or anti-parallel with respect to orbital angular momentum. Whereas this A in these coefficients can take positive value or negative value, depends on the rotation. If it takes positive value, which means it is co-rotating, the black hole is co-rotating. If it is negative value, then it is counter-rotating. So here we have so this one equation or one solution which includes all sort of possibilities: the spin of the particle alignment parallel or anti-parallel, and the spin of the black hole co-rotating or counter-rotating. So everything is included here.
Sorry, sorry, Satish, there is a question from
yes, please.
Joseph. Joseph, if you want to ask the question, I can read also. Okay, there is also an additional conserved constant in Kerr, the Carter constant. Is it not useful here?
I have not used it here because at the moment I am dealing only the planar analysis. Carter constant will be used in the non-planar analysis, which will come at the end of this talk. I will come to that at the end of the talk. Okay, so now here I have for the first time I have given the exact solution of a spinning particle orbiting the Kerr black hole without approximating the spin of the particle and without approximating the spin of the black hole. So this is a complete generalization here. Of course, this should satisfy all the special cases. Suppose if we switch off the spin of the particle, then it obeys the case of test mass in Kerr. Suppose if we switch off the spin of the black hole, then it obeys the spinning particles in Schwarzschild. Suppose if we switch off spin of both the objects, then it obeys the test mass in Schwarzschild. So as it should be, it obeys all the special cases. So this is a complete solution and a complete general solution. So being described the circular orbit, now let us go into eccentric orbit. For extracting the eccentric orbit, we can start from the exact circular solution, which we obtained here, and we develop the eccentric orbit from the circular orbit solution. This is a very standard procedure in general relativity. Comparing to geodesics is the standard procedure, which is called as the method of geodesic deviations. And here, of course, the particles are carrying spin. Therefore, we generalize that procedure for spinning particles. Now, let us consider two solutions, X and X bar, are the two solutions of the circular orbit and this infinitesimally deviated eccentric orbit. And these two solutions must, of course, satisfy the original equations of motion. Then it's very straightforward to compute the differences between these dynamical quantities x, u, and sigma on each word line at equal proper time tau, as denoted by del x. With this, by imposing these conditions, we write down the first order word line coordinate deviations as shown here, where these are 10 coupled differential equations. The first equation is for orbital parameter, and the second is for the first is for 4 orbital parameters, and second is for spin 6 spin components. Therefore, totally 10. So we have to solve this together to understand the spinning particles in the plane as well as in non-plane. So let us first let us go to a simple case, or to start with, we start from the planar case. In the planar case, as we know that there is no motion perpendicular to the plane, all these theta components are 0, or the theta variations are 0. Since these theta variations are 0, these 10 equations reduces to 6. And fortunately, in the Kerr plane, we have two conserved quantities, energy and total angular momentum, therefore, which takes care of this deviation del sigma tr and del sigma r phi, as I have shown in the conserved quantities. So additionally, we can reduce 2 more equations. So out of 10 equations, we are left with only 4 independent equations, and that forms a coupled system as shown here, which needs to be solved together as a coupled system for obtaining the deviations del t, del phi, del r, del sigma t phi. So now if you look at that, this is a inhomogeneous equation where these coefficients alpha, beta, gamma, delta are nothing but constant functions, which are functions of the radius and the black hole spin and the particle spin. On the right hand side, this del eta and del epsilon says, the change in the total angular momentum and change in the total energy from the reference circular orbit. So suppose we are considering a special case. We are looking at an eccentric orbit, which has the same energy as that of circular orbit, which has the same angular momentum as that of reference circular orbit. Then this change del eta and del epsilon can be set equal to 0, which means the inhomogeneous part can be, the right hand side can be set equal to 0. We can deal with only the homogeneous part. By solving this homogeneous part, we quickly obtain that, we see that there are 3 zero modes, which are secular solutions for the orbital degrees of freedom. And there are 2 pairs of non-trivial periodic solutions, omega plus and minus square. Whereas this, we can get rid of these 3 zero modes because we are looking at a special case. That is, we are looking at a special orbit which has the same energy and same angular momentum as that of the reference circular orbit. Therefore, we can eliminate these 3 zero modes. We can deal only with these 2 pairs of non-trivial periodic solutions. But again, A and B are again functions of radius r and black hole spin A and particle spin sigma. So now, since we have obtained the frequency, it is very straightforward to write these deviations, del t, del phi, del r, del sigma t phi, as well as del sigma tr and del sigma r phi as a function of sine or cosine functions. And the complete first order Whirlwind solutions are given here for t phi r, t phi, sigma tr, sigma r phi as functions of proper time, where this first term in all the equations, ut, u phi r and sigma 0 tr, sigma 0 r phi are evaluated in this circular reference orbit. And the remaining terms are the deviated orbit. So the circular orbit plus deviated eccentric orbit gives the complete first order Whirlwind solutions. So this is a complete solution where these n's, this n plus minus and this capital N plus minus are nothing but the amplitudes. So which we will see it in an example. So now if we specifically, the most important thing and the interesting thing here is the radial deviation. Let us consider this radial deviation, especially this deviated part, except this capital R, let us consider this radially deviated part. Let us write down here the radial deviation from the circular orbit, where these n's are nothing but amplitudes as I mentioned, and this tau plus or minus is the constant of integration determining the relative phases of oscillation. Now, because our system has 2 characteristic frequency, omega plus and omega minus, the apastron and the periastron of the spinning particle orbiting the Kerr spacetime reaches different minima and different maxima after every revolution. This comes from this expression, which I will show in a more proper plot in the next slide. Before going to that, let us understand it physically, what happens here because of this double frequency. So let us again go back to our total angular momentum conservation, which is shown here, where this is the orbital angular momentum part and this is a spin angular momentum part. In fact, to understand it physically, let us go one step down to a more simpler case Schwarzschild, that is A equal to 0 in this expression. Then we write down eta is this, where this eta is the total angular momentum, which should be conserved throughout the motion of the particle. And m is, of course, mass of the particle, which is constant, and u phi is evaluated at the circular reference orbit, which is also constant. So the only variable parameter is radius and spin. So from this conservation law, what we see is, in the planar case, the spin of the particle, the direction of the spin of the particle is fixed. It should be either aligned parallel or anti-parallel. However, the magnitude of the spin varies. That is, spin sigma r phi varies. And for the change in the magnitude of the spin should be compensated by the change in the radius to keep the total angular momentum conserved. That's the reason we see different minima and different maxima. And let me show that with the 2 examples. Let us consider a spinning particle which is aligned parallel or prograde spin, orbiting in a counter-rotating, which is in the counter-rotating orbit of the Kerr black hole, which has a rotation a equal to minus m. And I choose the reference circular orbit r equal to 10m. And now if you plot this, you could see that the radius versus proper time, you could see that where 10m is a reference circular orbit, around this orbit, you could see that after every revolution, the particle is not only precessing, in addition to the precision, it also, the maxima and the minima varies rapidly. So which you could see from this thing. So this is nothing but the plot of this expression. So this is first example, and similarly, let us consider an anti-aligned spin, which is indicated by minus, which is which is in the co-rotating orbit of the Kerr black hole with the Kerr parameter a equal to 0.999 m, which is almost extremal, and the reference orbit we choose 1.9 m, and you could see that when the spinning particle is in the co-rotating orbit and it is closer to the horizon, it goes very rapidly compared to the counter-rotating orbit. You could see that how rapidly this is orbiting, and the maxima and the minima varies very rapid. So from this analysis, what we understand is when the spinning particle is orbiting in the Kerr black hole, the peristore not only presses but also varies rapidly in the radial direction. It depends on the magnitude and the direction of the spin of both the objects, the spin of the particle as well as spin of the black hole. And this is, we see this effect because of, for example, when the Mercury is orbiting around the sun, we don't see this effect because Mercury is almost in the same phase as that of sun. It is not a rapidly rotating object. Whereas in the case of compact objects like black holes or neutron stars, which spins very rapidly, and that spin effect creates this radial deviation. And that's the reason we get this effect in the compact objects. So this is one interesting result. Now let us get into the second interesting result, which is innermost stable circular orbit. So, we all know that when a test mass is orbiting the Schwarzschild spacetime, then the ISCO is a standard result, which is 6m. Suppose if the particle is spinning and they are orbiting around the Schwarzschild spacetime, depends on the spin of the particle, the ISCO varies. And here both the objects are spinning, which is much more complicated. The spin of the particle as well as spin of the black hole. Therefore, the ISCO depends on the spin orbit as well as spin-spin couplings. Now, since we have obtained this frequency from our analysis, planar analysis already, so now we look at the stability criterion to understand the ISCO. So from this, we know that the circular orbits are stable as long as the planar deviations display oscillatory behavior. That is, the particle will have stable and bound orbit only if this frequency is real and positive. If it is not real and positive for imaginary frequencies, it runs into exponential behavior and it is not a bound orbit anymore. So we cannot find the ISCO. So therefore, for having the bound orbit, this omega plus or minus square as well as omega plus or minus should be greater than or equal to 0 individually. And for this, these four conditions must be individually conserved for having this frequency omega plus or minus square is greater than or equal to 0. Now, being obtained these conditions, now let us plot these four conditions in a orange square plane, that is a radius versus angular momentum square. We do this because the circular orbit can be defined with three simple parameters: orbital angular momentum, spin angular momentum, and the radius. Therefore, we plot radius versus angular momentum here. By plotting that, we see that these conditions gives us this region, the shaded region, where you could see that this is a equal to 0, and the right hand side is nothing but a greater than 0, and this is b equal to 0 line, and this covers b greater than 0, and a square minus 4b equal to 0, and this whole region is covered by a square greater than or equal to 0. So all these four conditions are plotted here, and the common area which covers these four conditions is shown in this table. This gray region. Within this gray region, the particle can have stable and bound circular orbit. And these lines, alpha, beta, gamma, and delta, are nothing but isospin lines. That is, I choose for constant spin lines for different values of sigma over m, as shown with this equation. So by plotting that, this alpha, beta, gamma, delta passes through either b equal to 0 line or a square minus 4b equal to 0 line. So while it is passing through this b equal to 0, and the corresponding radius gives the radius of the ISCO. Therefore, by collecting the boundary of this line a b equal to 0 and a square minus 4b equal to 0, we can obtain the radius of the ISCO as a function of the particle spin, as shown here. For an example, a equal to minus m. This a equal to minus m is shown in the first curve L, right? So as written here, a equal to minus m. So I collect these boundaries along this b equal to 0 and a square minus 4 b equal to 0, and I have plotted here for different values of spin parameter sigma over m, and I found the corresponding radius. And similarly, we can do for any value of a can start from 0 to a equal to minus m. You can solve it for any value of a. Here in these curves B, C, D, E, F, G, H, I, J, K, L, I have plotted for 11 different values, starting from a equal to 0 to a equal to minus m in the intervals of 0.1. So from this, what we realize is, this sigma over m, when it is positive, which means the spin of the particle is aligned parallel, and the sigma over m is negative, the spin is aligned anti-parallel. So this implies that the curve says us that when the spin of the particle is aligned parallel, for increase in the magnitude of sigma over m, the radius of the ISCO decreases. And in the retrograde region, that is the particle spin is anti-parallelly aligned, for increase in the magnitude of spin sigma over m, the radius of the ISCO decreases. So that's an observation from here. So this is all about the counter-rotating orbits. Now let us get into the co-rotating orbit, which is the analysis is very similar. The only difference is here, the stable circular orbit, the region of the stable circular orbit increases, and all these isospin lines, alpha, beta, gamma, delta, passes through the b equal to 0. Whereas if you note, in case of counter rotation, it passes through both b equal to 0 line as well as a square minus 4b equal to 0. Whereas here, all the line passes through b equal to 0. So similarly, we have collected while this alpha, beta, gamma, delta isospin line passes through this b equal to 0, we collected the corresponding radius in the x-axis here, and we plotted here as sigma over m versus r ISCO over m for different values of co-rotation, starting from a equal to 0 to a equal to 0.7 in intervals of 0.1. That is, this is 0, a equal to 0, this is a equal to 0.1, 0.2, etc. goes up to a equal to 0.7. Here the observation is very similar as that of co-rotation. That is, the right-hand side sigma over m indicates the spin of the particle is aligned parallel. On the left-hand side, the spin of the particle aligned anti-parallel. So it says that for increase in the magnitude of sigma over m, the radius of the ISCO decreases. Here in the retrograde region, for increase in the magnitude of sigma over m, the spin angular momentum, basically, the radius of the ISCO decreases. So, in this plot, I have shown only up to 0.7, not the higher values. So I will come at the end. So why it is not done yet. So what I have done is here I have described the many co-rotating and counter-rotating orbits in a very elegant way, right? So now this is about planar analysis. We have obtained the circular orbit, and we have obtained the planar eccentric orbits, and we obtained the ISCO. And of course, what is more interesting will be the non-planar precisional orbit. Now let us again go back to our perturbation theory, which the 10 equations which I have shown here. So to start with, let us start from Schwarzschild. Even Schwarzschild, it's not completely understood for spinning particle case. In the case of Schwarzschild, thanks to the conservation, thanks to the spherical symmetry of the Schwarzschild, and that gives us 4 conserved quantities. The total energy, which gives a conserved quantity for sigma tr spin component, and the total angular momentum J, which gives a conserved quantity for sigma r phi, and sigma r theta and theta phi for r theta and theta phi. So these are 4 conserved quantities for these 4 spin components. And in addition to that, as we said in the introduction, that we have defined the pseudo-scalar spin dipole product, which helps now, which gives an additional conserved quantity for sigma t theta. So since we have 5 conserved quantities in the Schwarzschild space-time, these 10 coupled differential equations, it reduces to 5. By using the 5 equations, we can get rid of 5 equations. So, which I have shown here. The 4 equations are exactly same as that of Kerr case, a Kerr planar case, which looks exactly the same way. And the remaining one equation is the independent equation for del theta with the constant shift del t. Of course, the first 4 equations are coupled differential equations which needs to be solved together as we have solved for Kerr spacetime. So here I concentrate on the theta deviation, which governs the non-planar orbits. Right now, let us look into this equation explicitly. So after all, suppose if we forget this right hand side, this is nothing but a simple harmonic oscillator, right? Which is very easy to solve, and even with the right hand side, it is not very difficult. This is just a constant shift del d. Therefore, the straightforward solution for this complete equation is given as that the del theta as function of tau as given as here, where theta at tau equal to 0 and u theta at tau equal to 0 are nothing but the initial position and the initial angular velocity at a beginning time tau equal to 0. And omega p is the precessional frequency, which I will write here which I will show explicitly. Before that, since we have obtained this del theta variation by using these conserved quantities, del sigma, this for t theta, theta phi, r theta, we can straight away write down the complete first order Verlaine solution for non-planar orbits. So where this theta is the equation which comes from here, the solution of this, and the remaining equation comes from the conserved quantities. Thus, we have written down all the 10 equations for Schwarzschild. That is 6 equation I have already shown in the Kerr case. Of course, for a equal to 0, that will reduce to Schwarzschild. Additionally, here I have written 4 more equations. So I have written all the 10 deviations in a completely analytic way in a first order in the Verlaine perturbation theory. Now, again, let us go into this theta equation, which gives more interesting physical results. Let us look into this theta equation, the solution, right? So you see this. When you plot this, this theta tau gives us the precessional orbital motion. That is the spinning particle when it is orbiting around the Schwarzschild spacetime. It gives us the precession of the plane, as indicated by this plot. That's this theta of tau versus proper time tau over m, as it is a sinusoidal wave. So this gives us a precision. So this could be understood physically in a more interesting way. Let us go back to this conserved quantity again. As we know that this total angular momentum, eta must be conserved throughout the evolution. As we know, the small m and u phi are constants already. So here again, the spin can vary, the spin and the radius could vary, right? But here, since it is not within the plane, the variation of the spin in direction as well as magnitude should be compensated by the variation in the direction as well as magnitude of the orbital angular momentum. That is, when the spin direction and magnitude varies, this orbital angular momentum L also varies to keep the total angular momentum constant. After all, this L is nothing but this r square u phi, and this whole quantity is nothing but spin angular momentum, and this is the orbital angular momentum L. So both should vary to keep this total angular momentum conserved. So therefore, since the spin angular momentum varies, this orbital angular momentum is also varying. As a result, this orbital angular momentum sweeps a cone over a large period of time. That is nothing but the geodetic precision, and that has been described with a fully relativistic precessional frequency as written here. And this is the first time it's written in a fully relativistic analysis. So yeah. So now let us jump into the question which I was asked before. Of course, I have solved only the spinning particle in Schwarzschild spacetime. What is more interesting for the practical cases, for example, when this LISA mission, in 2034 or around 2035, when it comes to, when it starts sending the signal, we need to understand more about the compact objects orbiting around the supermassive black holes in the galactic centers. For that, we need to understand, of course, all the black holes in the galactic centers are spinning. All the black holes are spinning. So we need to understand Kerr spacetime. That's what eventually we need. To understand that, we need a Carter constant of motion for describing the spinning particles. But the problem is, if you note, throughout this analysis, I did not truncate my spin. I defined my spin tensor and I dealt with complete spin of the particle. And also I did not truncate the black hole spin either. I dealt with complete spin of black hole as well as the particle. Therefore, to do that, I need a Carter constant of motion, which will be of this form. So far, I am successful in achieving the first order in spin. That is, I obtained the coefficient of kappa, lambda, mu, nu, which I have not shown in this paper. That will be another paper or letter. So I have obtained the kappa, lambda, mu, nu, and what needs to be computed is this quantity, the spin-spin coupling with m, some quantity like m, mu, nu, kappa, lambda. This is yet to be completed to deal with complete spin. And of course, in the traditional approach, like Mathis and Papapetro, people deal with only the first order spin. They truncate the spin all the time from the very beginning, and they deal with first order spin. Such an a paper called The Conserved Quantities of Spin-induced Particles in General Relativity. So he gave it for the first order in spin, particularly for the Mathis and Papapetro formalism. Whereas I am interested in complete spin of this form to deal in our own formalism. So that's the reason I have not solved the non-planar orbits in Kerr spacetime yet. So before that, I need to solve this problem first to understand the non-planar orbits. So this is in my priority list next as an important project, because when you solve this is going to be a very important theorem in the literature of spinning particle dynamics. So meanwhile, apart from the results which I have shown now, we are also solving another project, and currently I'm writing with the biggest student of Ricardo, and his name is Josel Mendoca. So, and this is more interesting. So as I said, the brackets which I defined are model independent. I can choose any Hamiltonian. In my whole analysis, I have chosen only the minimal Hamiltonian. Now, with Josel, I have included additional complication, the spin-spin interaction with the background Riemann tensor, where this kappa is a gravimagnetic ratio. If you include this new additional term in the equation, in the Hamiltonian, then the equations of motion changes, obviously. Then we obtain the new set of equations of motion, whereas the first equation is same, which defines the covariant momentum is proportional to proper force velocity. And the second equation, in addition to the gravitational Lorentz force term, there is a term in which the spin tensor, this spin square term, couples with the gradient of the Riemann tensor. This is nothing but the gravitational Stern-Gerlach force, analogously. And in that sense, this kappa is the gravimagnetic ratio, right? And for black holes, it's equal to 1. And note that in the second equation, for the minimal term, the right-hand side was 0, because kappa was 0. And here, because of the new term, I get additional terms here. So we have derived these equations of motion. Now we are extracting the orbits like circular orbit, planar analysis, Perrier-Stone and ISCO, as well as non-planar orbit, a complete system like currently we are in writing, which you may expect at the end of October or beginning of November in archive. So these are the current projects which I have been working in IIP. So now let me summarize before you ask the questions. So what we have achieved, what I have shown in this talk or presented in the paper was, for the first time, without approximating the black hole spin and the particle spin, I have found the general circular orbit solution as an exact solution. And I found I have developed the planar eccentric orbits up to first order. And more interestingly, I found that the peristome, in addition to the peristome shift, there should be a radial deviation because of the rapid spin of the spinning particle in curved spacetime. And I have given the innermost stable circular orbits up to 0.7 in co-rotation and for all values in counter-rotation. And the reason I have given only up to 0.7 is beyond that it's more complicated, and that itself will be another project to focus more around the ergo region. You know, a lot of interesting physics happens around the ergo region. So more focus needs to be given and developed as a new project. So that's why I have stopped up to 0.7 there. So because we don't have the quarter constant of motion for the Kerr space time, I have reduced the complications to Schwarzschild space-time and given the non-planar eccentric orbits, a complete non-planar eccentric orbits up to first order. And eventually I have given a completely relativistic pressure frequency for describing the spinning particle in Schwarzschild. So yeah, thanks for listening, and you may ask the questions.
It's a lot, Satish. Very interesting. And now we can move to the questions. If there isn't, you can use the chat or raise your hand or.
Sorry, say it again.
So Dimitri, you have a question? Please go on.
Yeah, thank you very much, Satish, for your talk. And I think it seems like very interesting and important results. I wonder how this study compares with what people already know in study, for example, in gravitational wave physics, where they're supposed to study the motion of black holes, right? So, for example, you mentioned some interesting results which you do not observe for Mercury, but which would be important for physics in the process of coalescing of.
All right. So basically, I have been describing only the orbits. So naturally, once I understood the non-planar orbits in the Kerr space-time, then the immediate step is, of course, obtaining gravitational waves such that we can match with the LISA data. So that's the eventual interest. But before that, a lot of things needs to be done, even in the test particle limit. Even in the test particle limit, a lot of things are missing, and especially when it comes to the spin, it's a lot complicated. So eventually, I want to do gravitational waves. And for your another question, like I have not included the comparable masses. This framework is only for test particle limit, spinning particle limit. Because throughout this analysis, I have neglected the internal structure of the spinning object. If I want to consider as a comparable objects like Ricardo does, so I need to consider the internal structure. I can no longer neglect that, which is much more complicated, of course.
Right. So, but even before you studied the gravitational waves, I mean, perhaps people in gravitational waves, they have to know about motion in the first place, right? So, and they usually use numerical analysis. I don't know. So, how your study compares to what is already known? That was my question.
Well, at this, okay. So, what you are asking, like you are asking me to compare with the other approaches, or what was the question?
For example, you mentioned this effect of radial variation.
That's right. Yeah.
So, is it known for black holes? And,
Okay. So okay, I understood the question. So you see, in my approach, there is only one way of describing. I follow the spin tensor. I follow the world line where the spin tensor is covariantly constant. Whereas in the other approach, like Mathis and Pepper-Petro, they have n number of supplementary conditions called spin supplementary conditions. So, which means there is no unique way of description in their approach. Whereas in my case, there is only one way of description. in order to compare these two approaches, for example, between these two approaches and comparing this with experiments, we need to obtain the gravitational waves, which is a physical quantity. Once we obtain that, that you can match with the data or the gravitational waves. Then in the gravitational waves, if you see this indication of this radial deviation, then we can come to the conclusion that yes, such a new effect is happening there.
So you, in the end, you have a prediction for them. Is that right? So something.
Yes, it's a prediction. This is not the first time I'm predicting. We have already, with the 3 other collaborators, we have already predicted for spinning particles in Schwarzschild. That was the first paper in 2016. Now I have generalized it for Kerr. I have predicted it for Kerr.
Okay. Yeah, I think I understood. Thank you very much.
There is one more. Yeah, please go.
Yeah. Hello. Yeah, thank you for the talk. But I have a simple question. These orbits, are they outside the black hole or also going in? Because we know about this singularity there.
No, these are so far my analysis is outside the black hole.
Okay.
And it is going closer and closer to the horizon, not inside the black hole yet.
Okay, thank you. Safe space.
so that will be called as this ballistic orbit, which has been done for test mass in Schwarzschild, but more complicated cases are not done. To the best of my knowledge, the spinning particles are not done yet. That is another problem in the to-do list. Once I understood completely about the outer orbits, then I will go into the orbit which is falling inside the black hole.
Yeah, there's also something strange about time. We know that for black holes if you go in, but we'll see that then in the other orbits.
Sure.
Thank you.
Please, Edson, please go on.
Thank you. You see me? No?
Yeah.
Okay. Thank you for the talk. I was wondering if you, with this approach, you could generalize the Penrose effect in somehow using the spin of the particle.
No, I think it's possible. I think you are talking about the collision, right? Or the energy extraction in the ergo region, right?
Right.
Yeah.
Do you think it can be a generalization of? I mean, since you have a spin for the particle, how could the Penrose effect could be generalized in this case if you have?
Well, in the other approach, like Mathis and Petrov, people have been looking at it by using, even for spinning particle, they are studying this Penrose process in the ergo region. I think, well, it's one of my interests to look that problem in my approach. So the difference is, I believe I can still do a lot of analytical work here. Whereas in the other approach, people are doing only the numerical studies. They study the numerical way of this collision, etc. So they produce results. But for me, what I'm more interested is to clearly see in the equations what's happening there. So I believe I could do that. But I'm aware of the problem and I'm interested in the problem, but I have not solved it.
Okay. Can I ask one more question?
Sure.
When you have the equation of motion for the particle, it appears terms that depend on the curvature of the space-time in the geodesics. Wouldn't that violate the strong equivalence principle?
No,
because you have a curvature tensors that in a geodesics equation, and then you could not eliminate them by a coordinate transformation. Would be that a kind of problem, or would be usual?
No, I think it's not a problem. It does not violate any principle, actually.
But you mentioned something about no minimal coupling, in the sense that you have curvatures
Yes.
coupling with
That's right. I think you're talking about this equation. Yes. This
one of them, yes, would be that.
Yes.
And then things like that wouldn't violate the equivalence principle in the sense that you cannot eliminate the curvature features and in a point in the space-time, in the sense that you have a coupling with the curvature, because usually you have equations of motion in general relativity, you can eliminate the gravitational field locally by a choice of coordinate system. When you have a direct coupling with curvature,
as I said, we compute these equations of motion by computing this Hamiltonian, any chosen Hamiltonian. This should be conserved for a specific space-time manifold, like shown here. You see this J comma HSG, the bracket should be equal to 0. If this condition is satisfied, then it does not violate any principle, to the best of my knowledge.
Yeah, but in the first equation that you have the Hamiltonian on the top.
Yes.
The Hamiltonian at the top contains the usual term that is the coupling with the linear momentum or the momentum. And there is a second term that's a coupling with the curvature.
That's right. Even with the second term, it obeys this condition. That's why you see, I have mentioned HSG, Stern-Gerlach force, and this is also HSG. So it satisfies. Not only that, even you can include other terms like charge coupling with the electromagnetic field strength, and you can study spinning charged particle in Riemann-Nordstrom. Even such a Hamiltonian, even such an additional term satisfies this. I mean, it conserves this. So therefore, it's not violating anything.
All right, I see. Okay, thanks very much, Satish.
Sure.
Thanks.
So Joseph, please go on.
I was wondering, since the Dirac equation can be solved in the Kerr space-time, if one takes the iconal approximation of that equation, would one be able to make some progress with this problem? I don't know if I'm making myself clear.
Well, I think I don't understand it clearly. Sorry.
Let me try.
Sure.
I think Joseph, you are mute. Okay.
Yes, yeah. The Dirac equation in the Kerr background can be solved exactly.
Yes.
It has been done, for example, in Chandrasekhar's book. And if one takes the wave equation and then uses the iconal approximation, you would expect to get something like particle motion with spin, because the Dirac equation also describes spin. Yes. So I was wondering if it would help psi and write it as a rapidly varying phase times a slowly varying prefactor, just as we do in WKB approximation, because this problem is a limit of the other problem.
No, you are right. You are right. Actually, in our first letter, which I have shown in these first slides, so we have mentioned that we have mentioned that these are analogous as this Dirac equation deals with these subatomic particles, and here we treat with the macroscopic object. In a limit, in a classical limit, it reduces to our Poisson-Dirac brackets. So for subatomic particles, they have very similar Poisson-Dirac brackets.